All right, everybody, we are going to stop reviewing material and start into the college algebra material. So again, if you just took algebra 2, some of this should look familiar. If you took algebra 1, algebra 2, these things should look familiar. However, we're not going to treat it like review. It's going to be new college algebra material, and the pace in this class is kind of fast. So for right now, I've got the timer set for 40 minutes. So I'm going to try to keep this video to a 40-minute video. That would be less than the time I would have in a real classroom if you were meeting me face to face. So this should be about the lecture of what one, or the length of what one lecture would be in a Monday, Wednesday, Friday class. If it goes really fast and you're like, I can't take notes, you might want to watch it once and then go back and take notes. But I think you could probably just pause it and keep up pretty well. All right, so the title for the first section, or for this section of material, is 2.1, and it's called Functions. So it's chapter 2, section 1, and it's called Functions of Graphs, Functions and Graphs, I think. Okay, so first, before we go anywhere, we need a definition of function. Okay, a function is a relationship between two sets where every element of the input, element of the input corresponds to exactly one element of the output. Okay, so it's a little bit of a mathy definition. We'll get a little bit more about what exactly that means as we go along. But basically, if you're thinking about a function, an equation that we've worked with before, something like that, every x that I put into the function, every input, okay, now they don't have to be x's, that's why we're being really broad and general here, right? Oh, hang on just a second. Oh, sorry, my alarm was going off and I don't know why. Anyway, it's probably about to go off again, so sorry about that in advance. So it doesn't have to be x's and y's, but we know that one thing from the input has to correspond exactly to one thing from the output. In general, though, whenever we talk about functions and equations, a lot of times we use the letters x and y, right? So for our purposes, we're going to have something called the domain. That will be my x values, and that is my input. That's what I put into the equation to see what's going on. And we will call this the independent variable. Okay. And my pen is trying to run out on me. The independent variable. And the thing about the independent variable is that we can pick values for it, or we can change the values for it. That's what makes it independent. It's not tied down. Okay, so that's the independent variable. Sorry about that. That pin just died on me. The range is going to go with your y values, and that's going to be your output. And that's going to be your dependent variable. Okay, so for instance, if I say, how many of us are 5'3" tall, I just independently just chose that 5'3" tall. So the height there would be my independent variable. It's my input. And what I would get out, it would be my y, or my output. It would be the number of people who are 5'3" tall. So when I say how many of us are 5'3", if you're 5'3", you need to raise your hand or vote or whatever it is we're doing, right? I independently chose 5'3", but if that matches you, then you're going to have to, whether or not you raise your hand, depends on whether or not your height is what I just said, okay? If you're 5'7" and I say 5'3", then you're not gonna raise your hand, right? Or you're not gonna vote. You're gonna wait until I get up to 5'7", and then when I say 5'7", you'll say, oh, that's me. And that, whether or not you raise your hand then, that is dependent on the fact that now your height matches the input, okay? So we need to keep these straight, and I like to tell my students that whenever we see an ordered pair, right, a coordinate pair, however you want to think about that, it always goes in alphabetical order for us. So X comes first and then Y, alphabetically speaking. Or if you were making the T chart, where you would put in values for your X's and your Y's, again, the X is on the left-hand side and the Y is on the right-hand side. So I like to think alphabetically. A lot of times things in math match up with the alphabetical stuff. So when I look at this domain, I think, oh, D comes before range alphabetically. So the domain matches up with the X, which comes first, and the range, which comes second, matches up with the Y. And whenever we get to looking at graphs, which we'll do maybe this time, but maybe in the next session, when we start to looking at graphs, we know that the X-axis is the left to right, and the Y-axis is the vertical, okay, up and down. So when we start talking about domain, we're going to look from left to right on our graph, and when we start talking about range, we're going to look from the bottom up. So I always read my graphs left to right if I'm reading side to side, and I always read my graphs bottom up, bottom to top, let's say. So I start at the bottom and I work my way up. That way I'm always starting, because when I look at a number line, the negatives are on the left-hand side and the positives are on the right-hand side. And I want my numbers to be in numeric order. So negatives come first. So if I'm reading from left to right, I get my negatives first and my positives. And if I'm reading from bottom to top, here on my y-axis, my negatives are below and my positives are above. So if I read from bottom to top, I'm basically reading negative to positive. So if I always read left to right and bottom to top, then I'm always reading in the proper order. So that helps me whenever I start talking about domain and range and things like that. Okay, so let's talk real quickly about what a mapping looks like. A mapping is just whenever I have two groups and it looks something like this. Here's a group and here's a group, and we'll define those groups in just a second. And I am drawing arrows between them. Okay, that's called a mapping, or sometimes you'll see it called a relationship. All right, so I've got several that I want to talk about. So let's say we have several students. Let's say we've got Ann and we've got Bob and we've got Chuck. Okay, 3 students. And maybe Ann and Bob and Chuck, I picked those because I can call them A, B, and C here in a second without having to write out the names all the time. So this circle over here just represent the name. Okay, and maybe we want to map those to the age. Okay, so the question is, how many ages can Ann have? Again, this is independent and this is going to be dependent. So I want to match her, Ann. I'm picking Ann right now, and I want to match her over here with an age. I don't know, maybe she's 21. Okay. The question is, can Ann have more than one age? Hopefully the answer is no, of course they can't. So name Ann is matched to one age. I can't say, oh, I don't know, maybe Ann is 21 and 25. I can't do that, right? So Ann gets one age. That's all she gets. And I can only match her element here only matches with one over here. Bob, maybe he is 18. Okay. Again, he can only match with one age. He only gets one age right now. If his birthday's tomorrow, he changes ages tomorrow, right? Okay, so he only gets one age. But then, so is this okay so far? Each element in the input is matching with each one element in the output. But then let's say I come down here and I talk about Chuck, and Chuck is also 19, or I'm sorry, 18 was the age I picked. Chuck is also 18. So let's think about that for just a second. Now my age is repeating, okay? So the question becomes, is it okay for the output to repeat? Okay. Is it okay for the output to repeat? It is, and still be a function, still a function, question mark. That's what I'm wanting to know here. Okay, so remember my definition way up here at the top was that every element in the input corresponds with exactly one element in the output. Okay, so the answer is actually, we don't care if the Y values or the outputs or whatever are repeating. Okay, that's all right. Bob can be 18, Chuck can be 18. I mean, Ann could have been 18. It didn't have to be a separate age. What I can't have is I can't be saying Ann can be 21 or Ann is 18. That's not a function. Okay, so the answer is it's okay for the output to repeat. Yes, that's all right. And yes, it's still a function. When you're going to be in trouble, the input cannot repeat. And remember, most of the time, that's our X's, right? The input cannot repeat. So let's, and still be a function. If the input repeats, it is not a function. Okay, that's what we're saying. So let's look at an example of that. So let's still use Ann and Bob and Chuck. So I'm still using name over here. Ann and Bob and Chuck, same input. And I'm going to match them with a group over here. And this time we're going to say addresses. Just addresses. Okay, so when I look at that, I'm saying, okay, Ann's address is in Commerce. She's got a house in Commerce. And Bob has a house in Greenville. Okay, so we're mapping right there, 1-to-1. This is okay. Bob gets exactly one address. But then we get to Chuck, and Chuck, his family has a little bit more money, and they have a house in Greenville, which again, we don't care if the output is repeating, but Chuck's family also has a vacation home or something, weekend home or whatever you want to call it, at the lake house. And sometimes he uses that as an address. So Chuck has 2 houses, his family does. Okay. So when I look at that and I consider looking at my inputs versus my outputs, Chuck has 2 arrows coming out of him. Okay. And so like if I were to list this like an ordered pair, it would be like Ann has a house in Commerce. Okay, no worries. Bob has a house in Greenville. Okay, that's all right. But Chuck has a house in Commerce or in Greenville. And Chuck has a house, I meant to say Lake Fork, I'm sorry. Lake house at Lake Fork is what I was thinking. He has a house in Lake Fork. So when we look at this as if it was ordered pairs and the input here only listed once, that's all right. Bob only listed once, that's all right. And similar thing up here, I didn't make the points, but if I had done them here, it would be like, I'm sorry for backtracking, Ann at 21, Bob at 18, Chuck at 18. Okay, up there, I'm okay because Ann gets 1 age, Bob gets 1 age, Chuck gets 1 age. So Chuck is only once here. But now when I look at it for addresses, I see that Chuck has 2 different points. So Chuck could be at Greenville or he could be at Lake Fork. Okay, I don't know where Chuck is right now. That's kind of a problem. Okay, so whenever I see that if the input repeats, then it's not a function. Not a function. I already wrote that down. Okay, so that's what we're watching out for. We can say stuff like phone numbers. People might have a work phone number, a cell phone number, and some people still have landlines. So they might have 2 or 3 phone numbers, right? I have a friend who actually has a cell phone that's her personal cell phone and a cell phone that's for work. So she by herself has 2 cell phones. And by the way, all it takes here is 1 counterexample. Okay, that's an important point. If this happens at all, even once, it throws you out of being a function. It's not a function. Okay. If we find any counterexample, then it's not a function. So for phones, I don't have to go through a whole bunch of people. My friend that has the 2 phones automatically has 2 different phone numbers and says that phones would not represent a function. Okay, so phones, not a function. Addresses, not a function. Your age is a function. What about this one? Think about it for a second. What if I had a group over here, name and social security number? Think about that. What do we know about your social security number? It's supposed to be what? Unique to yourself is what I hear in my brain. You say your social security number is supposed to be unique to yourself. So when I had things coming across like this, and Bob and Chuck, I would not have any kind of repetition. Chuck's not going to have this social security number or that social security number, right? He can do that with addresses. He can do that with phones, but he can't do that with social security numbers. So we think, or I hope we think, that social security numbers are a function. And you've got lots of stuff. It doesn't have to be people, by the way. What if I said all the states in the United States and their capital? All the states in the United States and their capital. And so I say Texas, and you say, once I say Texas, you're forced to say Austin, right? You don't get a choice. That's Texas's capital, so that's the dependent thing. And I don't know a bunch of other ones. So I know some of them, but I'm on the spot here. So whatever state we go, here's their capital. Whatever state, here's their capital. Are any of them going to say, well, is Texas going to say, well, I don't know, maybe our capital's in Austin, maybe our capital's in Houston, maybe it's in Dallas? No, we're not going to get repetitions of the input there, the Texas. It only gets 1 capital. So hopefully you see that should be a function, right? All right, what if it's an equation? So these are the when it's a mapping, these up here. What about an equation? You're going to see stuff that looks like y equals 3x plus 7. Okay. Y equals x squared minus 5. Okay. And y squared equals x plus 3. All right. So 2 of these are functions, 1 is not. Hopefully you've seen enough before that you know the one that is not a function, I'm going to just tell you right off the bat, is this third one. The other 2 are functions. But if you're not sure, then what you can do is you can substitute in numbers. That's the first check. Like I'm going to pick my independent variable here. I'm going to pick 2. Or you could pick 3 or whatever. I'm going to pick 2. Okay, so when I put 2 as an input into this function, I get, and I'm going to go ahead and introduce some function notation. So f of x means a function where x is the variable. Okay. We've got some function. We're naming it f function. It could be g, it could be h, whatever. Okay. And the variable in it is x. It could just as easily be something like g with a parentheses t, and your variable there will be t. Okay. So when I do this, I'm going to substitute in 2. If my function, I'm sorry, if this is my function, the y guy here at the beginning, then I'm going to put in a 2, which means everywhere I see an x, I'm going to substitute in a 2. 3 times 2 plus 7. That's the math that's going on here. Okay, so if you're substituting in, we're going to substitute in the 2. I use the function notation. By the way, anytime you see this function notation, if you don't like it, you can mark it out and say that's a y. Okay, or if you don't like the y notation, you can mark that out and say that's f of x. So we interchangeably use function notation equal to y, as long as we know it's really a function. So we're going to check that when we get down here to the third one. But as long as we know it's really a function, we're okay to interchangeably use them. So 3 times 2 is 6, 7 plus 7 is 13. How many answers did I get, or outputs did I get? Just 1, right? Okay, let's try this next one. I'm going to call him g of x just so he looks a little bit different. G of 2 is, sticking a 2, 2 squared. Everywhere I see an x, I'm plugging in a 2. 2 squared minus 5. So now this is 2 squared is 4 minus 5. I get a -1. How many answers is that? It's only one output, right? Okay. So I think I'm getting one output there. Now I will remind you, even if I start getting some that only have one output, it's possible that guy could be still not a function, because all it takes is one place for it not to work for me. Okay. But for now, we're going to check it and see. All right, so we're going to assume that if I get just one value, it's going to be that. I'll show you how to actually do the math in a little bit. Okay, so here we go. I want to put in 2 for this guy on where the x is, but I've got a little bit of a problem. Both of these were solved for y. This one's not solved for y. So before I go and plug in my 2, I need to solve for y. And if you'll remember, that's a y squared. And we said the other day that the opposite operation for squaring is square rooting. Everybody remember that? So I need to square root both sides. And then we said, but wait a minute, it could be 2 squared gives me 4, or it could be -2 times -2 gives me 4. So I don't know if this is a plus or a minus. When you put in the square root, you need to put in a plus or minus. And this is why I knew this guy was not going to be a function. Okay, because really what I've got is y equals plus or minus the square root of x plus 3. All right. And that plus or minus is where the uncertainty is going to come in. You'll notice I didn't even put in a function notation yet. If you wanted to, you could say, can it be h of x? But it's not going to be. So I'm not even putting in function notation. Let's check what this looks like. When I put in, let me go back to red just so it's the same. Plus or minus the square root of 2 plus 3, I get plus or minus the square root of 5. And that is 2 answers. So if you're not sure, that is a positive square root of 5 and a negative square root of 5. You can split them up so you can see that's actually 2 answers. So what this is telling me as an ordered pair is when I put in 2, I got out the square root of 5. And when I put in 2, I got out the negative square root of 5. That's a problem, right? I can't have that. I'm going to exit out. That's a problem, not a function. So in general, if I see a y squared or any even number there, it could be y to the 4th, y to the 6th, whatever, then I know that when I take that square root or the 4th root or whatever, I'm going to have a plus or minus, and that's going to mess me up. So that's why I knew when I just looked at it, oh, this is a problem because the y is squared. That's a problem. All right. Okay, yeah, we're okay. Let's try real quickly some substitutions because I've done several here. I want to make sure everybody's okay with it. So there is examples in your book, and I've got a few here of my own. So example 1 here for me says, think about the fact that f of x equals 2x squared minus 3x. They're giving me this. And they've done a couple of things here. First of all, I've got my equation that I'm going to plug into. And second of all, they went ahead and put in the function notation. When they do that, that tells me that they are confident that this is a function. So I don't need to go check it. It's already been noted in the book. This is a function. Now, if you wanted to look at it for a second, compare this one to this x squared minus 5 that we did earlier. Those are quadratics, right? That's a parabola. And so we know those are going to be functions. They're going to be okay. We'll look at graphs later. Okay, but this is a function. They're telling me that when they put that notation in. And they say, find a value for f of 3. Okay, so again, a couple of things. When they say a value, that means I'm going to get a number out normally, right? It could have some x's and stuff like that, but I'm not looking for any kind of weird, I don't know, coordinate system, coordinated points, anything like that. So when it says find a value for f of 3, that literally means come up here to where you have your function value, and where you see an x, substitute in a 3. Everywhere I see an x. So I'm going to go 2 times 3 squared minus 3 times 3. And I'm going to kind of caution you a little bit. You should start putting parentheses whenever you substitute. It doesn't matter here because this is a positive 3, but later whenever I have either a negative or maybe I have a binomial, an x minus 3 or something like that, whenever I have stuff that's more complicated, those parentheses are going to pay off for you because otherwise we miss things. So watch out, try to be as careful as possible here. And we're going to do this real quickly. So 3 squared, remember your PEMDAS, right? Please excuse my dear Aunt Sally, which is do your parentheses first, then your exponents, then your multiplication and division. Those are together, left to right. Then your addition and subtraction together, left to right, okay? So the first thing I see is an exponent. 3 squared is 9. So 2 times 9, and it's minus 3 times 3, or you can go ahead and multiply that if you want to. I just saw that I have multiplication here, so I was gonna wait. So 18 minus 9. Everybody see that? Multiply it out real fast. And now I just have a subtraction problem, so that's gonna be 9. I have a value, yeah. That's my value for f of 3. So f of 3 equals 9. If you wanted to write it like that, you could. Or you could write it down here. F of 3 equals 9. Okay. All right, so another one. How about, I'm gonna rewrite my thing here. My function was 2x squared minus 3x. How about if it was 3f of x? Okay, find a value. Now, I'm not substituting in here. Instead, I'm what? I'm saying take your entire function, f of x, that's the entire function, right? And what? Multiply it by 3. So that's going to look like 3. And again, I'm going to use the parentheses, 2x squared minus 3x. And then remember that whenever you're multiplying this stuff, you have to distribute. So the 3 times the 2x squared and the 3 times the negative 3x. So I'm going to go one little step over here and I'm going to say that's 6x squared minus 9x. Oops, 9. Sorry about that. Okay. 6x squared minus 9x. So it just depends on what they ask me to do. My next one, this is where I cautioned you, so let's watch out for it. We're still going to use the same function, so I'm just rewriting it. If you don't want to rewrite it every time, you don't have to. Just remember what the original function was. The next one says find f of negative x. Okay, so again, what they've done is they've replaced x with negative x. So I'm going to come through here and everywhere I see an x, I'm going to replace it with negative x. Now, if it starts getting complicated and it bugs you, here's what I've told students before, because this is something being squared and then multiplied by 2. You can do this. Go through and everywhere you see an x, put your parentheses. I know it's going to be 2 times something squared minus 3. So just copy everything down and go ahead and put your parentheses. And then we'll come back and fill it in. Okay. This guy is going to be where I had an x up here in the parentheses. And this guy is going to be where I had an x up there in the parentheses. So the question was, what did we replace the x with? Well, they replaced it with a negative x, right? Negative x, negative x. And now we'll see where these parentheses are going to really start coming in play, because for instance here, if I just wrote -3, negative x, we would think that's a subtraction problem, right? We have to remember it's a multiplication. And I've got a negative times a negative there now, right? So we talked the other day, f of negative x equals, we talked the other day about the fact that a negative times a negative is a positive, right? So negative x is all being squared. That means the negative times the negative, right? And the x times the x. So when you multiply this, you've got 2, a negative and a negative is a positive, x squared. And then here I've got -3 times negative x, which is also a positive, which is 3x. Okay. There was my answer up there. Sorry about that. Okay, that's what it looks like when I subtract, or when I substitute a negative inside. What if they ask me for this? So I'm just going through a lot of what ifs. What if it was this? What if it was that? What if they said, again, same function, 2x squared minus 3x. What if they said find negative f of x? What are they asking me to do? I want you to think to yourself when you see stuff like this, what are they asking me to do? Okay, my f of x is all of this. They're not substituting into the f of x, right? They're multiplying the entire function by a negative. So this is going to look like negative parentheses, substitute in your f of x. Okay, so all of that f of x guy needs to be negative, right? The opposite of what it was before. Okay, but again, whenever I see that, I go, oh, stinker, I'm going to have to distribute that negative sign through. Okay, when I do that, -2x squared, right? And a negative times a negative becomes a positive 3x. So notice here, substituting a negative inside of the function is not necessarily going to give me the same answer if I substitute a negative on the outside. The 3x's are both positive, but the 2x squared here is positive and here it's negative. So that is not the same thing. So it really does matter where I put that negative. All right, and then they're going to do some crazy stuff to us. So for instance, they're going to ask us, and this will be in your homework on the computer, right, in the my math lab. So then they're going to, here's this example. F of x is still 2x squared minus 3x. I'm not changing that on us. What if I asked you to find f of x plus f of 3? And it's almost always find. Okay, find f of x plus f of 3. Okay, this is actually 2 steps that they're asking me to do, right? The first one is put in your original function. Okay, I can do that. Then add it to f of 3. So we're going to have to find f of 3. But wait a minute. We did f of 3 earlier, right? We said that f of 3, because it had a number putting into it, actually gave me a number back out, which was 9, right? So I actually found an actual value for that. These that I've done recently, they didn't give me a number, so I've had these x's hanging around, right? So I know f of 3 is 9 because we already did that. So this is what it's going to look like. Put in your f of x. Okay, there's my f of x, 2x squared minus 3x. Boom, put parentheses, plus, put in your f of 3, but we know f of 3 is 9. So plus, and you can put parentheses here, but when you're adding, it doesn't matter, unless it's a negative, you'll want that, maybe, plus 9. So this actually becomes 2x squared minus 3x plus 9. And this guy's a square, this guy doesn't have a square, his exponent's really a 1. And this 9 doesn't have an x on it at all. So all three of those are different terms. We cannot combine them. So that is my simplified form. That's it. Yay. All right. One more thing whenever we start. So we're going to do domain real quickly because I need you to do that so you can do your homework. So domain and range, we said domain was my inputs or the values of x's that I could get, and the range is the outputs or anything that comes out of it. And when we do graphs on the next one, we'll see, oh, graphs, we can look at it and see the graph is a little bit different and we'll follow it pictorially. But there is a way for me to find the domain in a function using the actual equation, basically. Okay, that's the one that wasn't working. Need to throw that one away. All right, find the domain in a function. Remember this. There are two things that you should not be doing in algebra, okay? So 2 things you can't do. Remember this. You can't divide by 0, right? Why is that? If I punch in my calculator, 5 divided by 0, what do I get? It'll tell me undefined or error, right? So that is an undefined function. And if you get into calculus later, you might find out that sometimes you can divide by 0. But for us, for our algebraic purposes, we can't divide by 0. So we're going to watch out for stuff like that. And I can't take an even root of a number. Okay, so a square root, a fourth root, whatever, if that number inside of the radical is negative. Okay, and we may actually have heard of imaginary numbers before. We'll deal with those later. But for our purposes, when we're looking for domain, we're looking at real numbers, things I can put on the number line, right? So I'm looking at all of my x values. Here's my 0. So when I'm looking at domain, I want real numbers that are going to work for me. And whenever I go to plug in or to plot an imaginary number, which is what taking a square root or a fourth root of a negative number does, if I go to plot an imaginary number, I can't do it on the real number line, which means that that can't be an x value or an input value for my domain. So those are the things I'm going to watch out for. Real quickly, I've got about 4 little examples. I think we can do them pretty fast. I know I'm running low on time. What if we had something like this? F of x equals x plus 3. This is my next example. Sorry. X plus 3 divided by x minus 5. Okay. We just said we can't divide by 0. So, question. Do we care about the top? About the numerator? Do we care about the top? No. What we care about, yeah, I hear you saying it, so I hope you're saying it. What we care about is that this, no. Okay. We care about x minus 5 cannot equal 0. And when I do this, I literally write it just like I just wrote it there. And that's what I want my students to do. I want you to write the denominator, whatever it is, cannot equal 0, because if it's 0, I'll put a 0 down there and now I'm dividing by 0 and I'm going to cause problems, right? So now a lot of the time when I look at this, this becomes a linear equation and I can solve those, right? So this is not bad whenever I go to solve this. you treat this does not equals just like you would treat an equal sign or an inequality. It is literally one of the inequalities. So how can I solve this guy? Add 5, add 5, right? X cannot be 5. And if I look at it, sure enough, 5 minus 5 would give me 0. And that is the problem. So when I go to look at domain, I can say domain can be all x's, the set of all x's, such that x is a real number, but x does not equal 5. Now that's the very mathy way to put that. Okay. If you were doing this on interval notation, which is this is set builder notation, you're probably going to need to do interval notation in your homework and stuff like that. That would look like, okay, I can do all of these x's, 0, 1, 2, 3, 4, 5. I can do all of them except for what? I can't do 5. So 5 is an open circle. I can do all these negatives and I can do all those positives, but I can't do 5. So when I go to do interval notation, I need to be able to mark that guy out and say, all right, what is this? Left to right. Remember, we're always reading like a book, left to right. Negative infinity is down here. Does everybody agree? Positive infinity is way up there, going that direction. And everything in there is okay except for the 5, right? So interval notation says I can go from -5, follow. My gap is right here at 5. I can't use 5, and we'll talk about what's in there in a minute. And then we can go from 5 to positive infinity, right? So if you know about interval notation, and hopefully you do, we know that we've got those hard brackets for included and the parentheses for not included. And we want to know, can we ever truly reach infinities? Nope. So those get parentheses. And what about the 5? 5 was an open circle, so it's not included. So when it's not included, we put a parenthesis. If it was an included point, it would be a hard bracket. And I usually tell people, it's like when it's equal, you use the hard bracket and they look similar, right? So when it's equal, you use the hard bracket, but this is not equal, so I use the little parentheses. And then one more thing, just to make your interval notation complete, we put the union in the middle because that means it can be anything over here or it can be anything over here, okay? So I just ran out of time, but I want to real quickly do one more where we're worried about domain in the bottom, and then we'll worry about square roots next time. Okay, so I'll make another video for that basically. G of x equals 5 over 2x plus 6. Again, do we care about the top? No, Dr. Webster, we don't care about the top. What we care about is 2x plus 6 is on the denominator and it can't be 0. So real quickly, go solve that for yourself. I'm going to run it real fast. If you need to pause, then pause. I would subtract 6 and those would go away. I would get 2x cannot equal -6. And then to get the x completely by itself, I would divide by 2, and I would say x cannot equal -3. So again, everything's okay on the whole entire number line except for the -3. So negative infinity is okay up to -3, but I'm not going to include that because it's a bad spot, all the way up to positive infinity, okay, which is also not included. So your number line would look something like this if you were doing it. You don't always have to do it. I'm just showing you what happens. The -3 is not included, but all this other stuff is. Again, left to right, negative infinity all the way up to -3. There's that. Or -3 all the way up to positive infinity. And I know I'm over time, I apologize. And that is the basics of functions and domains and range. So I will get you another video and I hope this all makes sense. Let me know if you have questions. Thanks. Bye.